single phase semiconverter with RL load. In practice, a load has a finite inductance. The load current depends on the values of the load resistance R and the load inductor L. And we know the operation of a single phase semiconverter. Please refer the previous video. The link is also given in the description. When the supply is given in the positive half cycle, T1 and D2 operates and the current flows through the load. And when T1 is fired at alpha, voltage appears across output. In negative half cycle, T2 is triggered at pi plus alpha and the input voltage appears across the output voltage, but the current is continuous. This is due to a freewheeling diode and this is also due to freewheeling diode. Other two parts are due to thyristor conduction. The converter operation can be divided into two modes, that is mode 1. This mode is valid between 0 less than omega t less than alpha, during which the freewheeling diode Dm conducts. The load current IL1 during the mode 1 is described by L di by dt plus R IL plus E equals to output voltage from 0 to pi is 0. Now, with initial conditions that IL1 at omega t equals to 0 equals to capital IL1 in the steady state. This is our initial condition of the current. Then IL1 is given by IL0 e to the power of minus R by L of t minus E by R 1 minus e to the power of minus R by L of t. Let this be equation number 1. At the end of this mode, that is at omega t equals to alpha, the load current becomes IL1. IL1 equals to IL1 at omega t equals to alpha is equals to IL0 e to the power of minus R by L. From this, omega t equals to alpha, then t equals to alpha by omega. So, multiplied by alpha by omega minus E by R 1 minus e to the power of minus R by L alpha by omega. This is for IL1 greater than or equal to 0. That is equation number 2. So we got the two equations in mode 1, 0 and alpha and at alpha. Now mode 2, this is valid between alpha less than or equal to omega t less than or equal to pi, while the thyristor T1 conducts. Vs equals to root 2 Vs sine omega t is the input voltage. Now the load current IL of mode 2 is given by L d IL2 divided by dt is the voltage across the inductor plus voltage across the resistor plus E equals to input voltage, that is root 2 V sine omega t. Solution that IL2 equals to root 2 Vs divided by Z sine omega t minus theta plus A1 e to the power of minus R divided by L into T minus E by R for IL2 greater than or equal to 0, where Z is equals to R square plus omega L whole square under the square root, and theta is equals to tan inverse of omega L by R. We have a constant here undefined, so we need to find out the constant given determined from the initial conditions at omega equals to alpha and IL2 equals to IL1. These are the initial conditions for the mode 2. Substituting in A1, we are going to get then A1 equals to IL1 plus E by R minus root 2 Vs by Z sine alpha minus theta e to the power of R by L, and we have a t for that initial conditions that omega t equals to alpha, so t equals to alpha by omega. Now substitute this A1 value in this equation, then you are going to get IL2 equals to root 2 Vs divided by Z sine omega t minus theta minus T by R plus A1, I am substituting this, IL1 plus E by R minus root 2 Vs by Z sine alpha minus theta of e to the power of r by L alpha by omega e to the power of minus r by L into t. Or else by combining this you can write e to the power of r by L is common, alpha by omega minus t. This is equation number 3. At the end of mode 2, the steady state condition, that is I L2 at omega t equals to pi is equals to I L0. Now applying this condition to the equation number 1 and solving for I LO, we get I L1 naught equals to root 2 Vs by Z sine pi minus theta minus sine alpha minus theta e to the power of r by L alpha minus pi divided by omega minus e by r divided by 1 minus e minus r by L pi by omega for IL naught greater than or equals 0 and theta is less than alpha less than pi. And this is equation number 4. Now we got the current equations. The first equation belongs to the first area, that is 0 to alpha, and second equation belongs to omega equal to alpha, and third equation belongs to alpha to pi, and the fourth equation belongs to initial conditions. The RMS current of thyristor can be found from third equation, since third equation belongs to the area between alpha and pi where the thyristor is on. I RMS equals to 1 by 2 pi integral alpha to pi I square L2 d omega t under the square root. Now the average current of a thyristor can be found from the equation number 3 again. I average equals to 1 by 2 pi integral alpha to pi I L2 d omega t. The RMS output current can be found from the equations 1 and 3. I naught RMS equals to 1 by 2 pi, that is 0 to alpha I square L1 d omega t plus 1 by 2 pi, that is alpha to pi I square L2 d omega t, whole thing under the square root. The average output current can be found from equation 1 and 3, that I naught average is given by 1 by 2 pi integral 0 to alpha I L1 d omega t plus 1 by 2 pi integral alpha to pi I L2 d omega t.